All right, let's talk about that moment. You know the one. You finally got your STM32 firmware running. The light is blinking, the motor is spinning, it works. But then that little voice in your head kicks in. Could this be better? Faster? Could it use less power? Well, today we're going to answer that question. We are moving beyond just getting code to work and diving deep into how to make it truly efficient.
So, here's how we're going to tackle this. First, we'll talk about why this stuff even matters. Then, we're going to grab the easiest win you can get, tweaking the compiler. From there, we'll get into the code itself with some smarter math tricks. Then comes the fun part, making the hardware do the heavy lifting for us. We'll wrap up by talking about interrupts for real-time response and putting it all together into a complete optimization mindset.
Okay, so let's start at the beginning. Why should we care about shaving off a few microseconds here and there? Well, in the embedded world, performance isn't just a vanity metric, it's everything. It directly impacts battery life, how responsive your product feels, and whether you can even get the job done on the hardware you've chosen.
And that leads to the big question you've got to ask yourself. Sure, your firmware works, but is it efficient? Because getting that LED to blink is just step one. The real engineering challenge is making it blink using the absolute minimum amount of energy and leaving your CPU with plenty of headroom to handle whatever comes next.
This brings us to what I think is the most important concept in modern embedded design, the race to sleep. And it's a beautifully simple idea. The faster you can get all your processing done, reading sensors, calculating, updating a display, the sooner you can put that microcontroller into a deep sleep mode, and that is where you save a ton of power.
Just look at this diagram. It illustrates the whole thing perfectly. See that little slice of process time? That's when your chip is awake and burning through your battery. Every optimization we do is about shrinking that slice. The smaller that active window gets, the longer the chip can spend in that inactive, low-power state. For anything that runs on a battery, this is the entire game.
All right, let's get our first win on the board. And the best part? You don't have to change a single line of your code to do it. We're talking about the compiler. It's all about just telling the toolchain what you actually want it to prioritize.
Now, when you're debugging, you're probably using OO, which means no optimization at all. But just by changing a simple flag, you can get a huge boost. O2 is a fantastic balanced option for speed. O3 goes even harder on speed, but be careful, it can sometimes make your code bigger. And my personal favorite for projects tight on memory, OS, which is optimized for size. It gives you almost all the speed of O2, but keeps the final binary as small as possible.
But wait, there's more. You can take it a step further with something called link time optimization, or LTO. See, normally the compiler looks at each of your C files one by one, in isolation. It's like trying to solve a puzzle by only looking at one piece at a time. LTO lets the compiler see the entire puzzle at the very end, allowing it to make much smarter optimizations across your whole project.
And just look at the payoff. On a real project, just flipping the switch on LTO shrunk the code size by 17%. That's almost 30 kilobytes of flash saved just by checking a box in your settings. That could literally be the difference between your project fitting on a chip or having to move to a bigger, more expensive one.
Okay, so we've squeezed all the easy juice out of the compiler. Now it's time to roll up our sleeves and look at the code itself. Because you'd be surprised how some seemingly innocent lines of math can absolutely destroy your performance, especially with floating point numbers.
Take a look at this. Seems totally normal, right? We're just doing some simple multiplication. But there is a hidden performance bomb in this line. By default, the C language treats a number like 2.092 as a double precision 64-bit number.
And the fix is just one single character. By adding that F at the end, you're explicitly telling the compiler, hey, treat this as a standard 32-bit float. So why does that matter? Well, the floating point unit, the FPU, on chips like the Cortex-M4 has dedicated hardware to do 32-bit float math super fast. If you don't add that F, you force the compiler to use slow software libraries to emulate 64-bit math, completely bypassing that speedy hardware.
And the difference is, well, staggering. Making that one tiny change took a processing loop from 30 milliseconds all the way down to under 5. That's a 6x speedup. So the takeaway here is huge. If you're using single precision floats, you must use the F suffix on your numbers, always. And this idea of using the right tool for the job goes way beyond simple math. If you're doing something heavy, like a digital filter or an FFT, please don't try to write it from scratch. ARM gives us the amazing CMSIS DSP library. It's a collection of functions that have been hand-optimized by experts to use every trick in the book, like the special signal processing instructions baked into the Cortex-M core.
How much better is it? Try 35 times faster. That's right, for a floating point FFT, using the library function instead of a generic C version is 35 times faster. It's an absolute game changer and probably the single biggest performance lever you can pull for complex math.
Which leads me to my absolute favorite topic, getting the hardware to do the work for you. You see, the CPU is great, but it's a generalist. STM32s are jam-packed with specialized hardware designed to do very specific things way more efficiently than the CPU ever could. Our goal is to offload as much work as possible so the CPU can just chill out, or better yet, go to sleep. And the king of offloading is DMA, or Direct Memory Access. The best way to think about DMA is like a little mail carrier inside your chip that just moves data around. Instead of the CPU wasting its time copying data byte by byte from, say, your ADC into memory, you just give the DMA controller a simple order. Move this block of data from here to there and just ping me when you're done. And poof, the CPU is totally free to do other things. But it's not just about moving data. Some STM32s have hardware for doing math, like the Cortex coprocessor. This thing is a beast. It's a specialized engine built to do one thing and one thing only: compute trig functions like sine and cosine super fast. This is the kind of math that's everywhere in motor control and other advanced applications.
And just look at the difference. A standard software library takes over 800 clock cycles to do a polar to rectangular conversion. The Cortex hardware, it does the exact same job in just 58 cycles. That is over 14 times faster. And while it's working, the CPU is completely free. This is the magic of hardware offloading.
All right, we've seen how hardware can be our best friend. Now let's switch gears back to software, specifically the heartbeat of any real-time system, the interrupt service routine, or ISR. When something important happens, like a button press, an ISR is what lets us react instantly. But how you write them is absolutely critical. This right here is the golden rule. If you remember one thing about interrupts, make it this. Your ISR needs to be fast, like lightning fast. Its only job should be to get in, do the absolute bare minimum, and get out. If you spend too much time in an ISR, you risk blocking other, more important interrupts, and that's how systems become unstable.
So how do we keep them lean and mean? Here's the playbook. First, never ever put heavy math or long loops inside an ISR. And it should go without saying, but absolutely no delays. The best practice is to just set a flag or drop a message in a queue and let your main loop handle the heavy lifting later on. Or, even better, have the interrupt just kick off a DMA transfer and let the hardware take care of everything.
Okay, we have covered a ton of ground, from high-level compiler settings all the way down to the nitty-gritty of hardware peripherals. So now, let's zoom out and put this all together into a complete, systematic way of thinking about performance.
And it all starts with this. If there's a mantra for optimization, it's measure, don't guess. You can't fix a problem if you don't know where it is. So you have to profile your code. Toggle a GPIO pin around a function and put it on a scope. Use the built-in cycle counter. It doesn't matter how you do it, but you must find out where your code is actually spending its time. Optimization without data is just a waste of time.
I love this pyramid because it gives you a roadmap. It's a whole philosophy. You start at the top, always. Profile first, to find your bottleneck. Once you know where to focus, work your way down. Start with the easy compiler wins. Then, look at your code and algorithms. Can you use a better library? Are you using floats correctly? After that, ask yourself, can I offload this to hardware? And finally, make sure your real-time architecture, your interrupts, are solid.
So there you have it. We've gone from the big picture all the way down to the bare metal. You now have a powerful framework to stop treating performance as an afterthought and start building it into your designs from day one. So the only question left is, what's the first bottleneck you're going to hunt down in your own project? Thanks so much for watching.
If you like this one, the YouTube algorithm says you're going to love my other videos, so go check them out.